Раз, два, три. Сергей Валерьевич, проверка звука. Слышно ли меня? Раз, два, три. Проверка звука. Сергей Валерьевич, слышно ли меня? Вот.
Уже слышно, да? Уже слышно.
Dear colleagues, please take your seats as we are trying to wait someone or not. We're going to start. So, do you remember where we just visited? What place during our technical tour? What is the name? Kurchatov Institute, sure. And Dr. Stanislav Subotin is from Kurchatov Institute. He is here with us with his lecture.
Thank
Please.
you. Do you listen to me? Yeah. Okay. Should I speak louder? Okay. Good. So, molten salt reactors, prospects, and problems. You see, molten salt reactors has rather long history. Recently, I saw this table of Mendeleev for nuclides, 150 years. Molten salt reactors, half of this time interval from 1950s. So history is rather good, positive. Until this time, there is no negative consequences of utilizing this technology. Excuse me, my English is not perfect. Maybe if you have a question, I would be grateful to you. But when we consider history, we should interest can be different. So we consider molten salt reactor as a part of nuclear energy system. And maybe you know that inside IAEA, International Nuclear Energy Agency, during, I think, 20 years, there was developed methodology of creating a nuclear energy system. And from that time, we consider nuclear installation not in the competition regime, that PWR is in competition with sodium-cooled reactor. No. Inside the system, we tried to make in such a way that they should be, all the reactors of the system should be in cooperation. So the main task of INPRO project on this text. For us, it's important that we should assess all the reactor directions from the point of view sustainability of the system. So, and the main task of, excuse me, and the main task of methodology of creating nuclear energy system is formulated as that future system may include evolutionary as well as innovative designs of nuclear facilities, PWR, BWR, fast breeder reactors, and we propose molten salt reactor too. But the task of this nuclear energy system to make a contribution to the energy production in 21st century, and nuclear energy should help us to save organic fuel. And nuclear energy should be rather large scale and to meet requirements of sustainable development. At the same time, it was another attempts to develop nuclear energy system, International Forum Generation 4. So, and specialist who was going to give you this lecture, unfortunately in Vienna now, in Austria, they have a last meeting for Generation 4 concerning molten salt reactors. So you can see that at that time it was the beginning of our millennium. among 100 of reactor directions was chosen 6 directions for future development. Among them, molten salt reactor. We have no time to discuss every, but you see that molten salt reactor has a very good perspective from the international scientific society. So I told you that innovative nuclear energy system will have evolutionary design of different reactors, advanced PW, BW, new designs of lead-cooled reactor, sodium-cooled reactor, supercritical water-cooled reactor, and molten salt reactor too. We consider molten salt reactor goals, purposes, and problems. So, before this project, in 1989, in Kurchatov Institute, we decided to investigate all the reactor directions, and we tried to find any perfect design of reactor which can meet all our requirements and to reach all our goals. When we consider thermal reactors, fast reactors with solid fuels, and then molten salt reactor, we went to conclusion that there is no possibility to create perfect one directions, and we should consider system. And we tried to investigate, as I remember, approximately 9 problems. I show you this only 4 problems, and you see thermal reactors can meet only various fields of energy production for electricity, for heat, for industries. Fast reactors rather suitable for increasing resource base for utilizing of uranium-238, not only uranium-235. But what to do with minor actinides, and what to do when we will be lucky with receiving a new energy resource like fusion, maybe we should demonstrate that we have opportunity to close nuclear energy to consume all dangerous nuclides. And in this case, only molten salt reactors, I mean reactors with liquid fuel, can permit us to consume all nuclides which are not suitable for solid fueled reactors. So there was a conclusion that for future we should consider system, not definite type of reactors. In this case, we should find some way, not economical mechanism to develop a nuclear energy system without competition. There should be some system in which every type of reactors should help other types of reactor to meet our acceptable future. So after this, we decided to make, you see, when I have some idea, I should investigate different type of theories, knowledge, and so on, and try to make special models for scenarios analysis with help of different scenarios. We tried to create some special computer codes for system investigations, and we consider that system include nuclear fuel cycle is basement of the nuclear energy system, not any type of reactors, but nuclear fuel cycle corresponding technologies is a basis. Without basis, no development. So, and then thermal reactors variety of thermal reactors. Small capacity, medium capacity, large capacity, PWR, BWR, high temperature gas cooled reactors, and so on. And fast reactors. Different types of sodium cooled, gas cooled, lead, bismuth cooled, lead cooled, and supercritical water cooled reactor. And molten salt reactors. And molten salt reactors at the time we consider as a burner for minor actinides. Because now we consume only uranium-235, and we are rather lucky that we have enough uranium-235. But if we consider sustainable development, uranium-235 we should consider as neutron source, not the energy resources. Energy resources is uranium-238 and thorium-232. But we need neutrons. The only acceptable for energy production neutron source is only uranium-235. No accelerator, no fusion. And so we should consider as like a grain, not for eating, but for putting the earth and to have a large scale nuclear energy system. So it's very important. Uranium-235 is a neutron source. And now we consume this neutron source for energy production. It's not good. So what we have now, it's not very good for our future. So our task to create nuclear fuel cycle for efficient utilization uranium-238 and thorium-232. But if I would like to utilize uranium-238, I produce minor actinides. So there's no way to eliminate them. When I closed fuel cycle, I produce plutonium. Now, when we have uranium, when we have PWR, I can, for 1 gigawatt year, I consume one ton of heavy nuclides, uranium-235, and produce about 200 kilos of plutonium, and maybe 40 kilos of minor actinides, neptunium, americium, and curium. So if plutonium we are going to utilize for energy production, but we don't know what to do with minor actinides. Maybe it's a very valuable nuclides for our future, for medicine and so on, because it's not a waste. We simply we have no efficient technology for utilization. And in this case, molten salt reactor is only acceptable uranium reactor direction in which we can consume minor actinides. So energy resources and neutron resources. Deuterium and lithium is very good when we will receive a fusion technology. But unfortunately, we have a perspective, but no such technology in our hand until. So uranium-235 is only neutron source. It's important. So for modeling of situation with neutron balance in a nuclear energy system, we have such scheme. Different kinds of thermal reactors, different kinds of fast reactors, and molten salt reactors. For what we consider these reactors? We consider these reactor for utilization of minor actinides. And in system, our goal is not to burn minor actinides, but to make a closed fuel cycle for minor actinides. As we have, with help of fast reactors, efficient closed fuel cycle for plutonium, molten salt reactor we are going to use for efficient closing fuel cycle for minor actinides. We have no opportunity to burn it for to zero. And our task to minimize the quantity of minor actinides in fuel cycle. So you can see the roles of different reactors. And for liquid fuel reactors, we consider the goal to minimizing of amounts of minor actinides within the nuclear energy system. For thermal reactors, you can read that they have a lot of applications, and there is, and you can maybe you can read that fast reactors can meet all the requirements. No, unfortunately, we should have a lot of different kinds of thermal reactors, and we should have at least two types of fast reactors, because if we are going to have only one technology, it's very dangerous. We should have at least two directions. And fusion neutron source. Fusion neutron source, we consider that fusion for the nearest future, maybe for 100 years, we have no opportunity to receive a positive balance of energy. But fusion neutron with energy neutron 40 megaelectron volts is rather good for conversion thorium 232 in uranium 233. We have very interesting reactions N neutron and neutron 2 neutron. We know losing. We know we can produce uranium 233 without losing the neutrons. And these reactions, especially N to 2N, can permit us to produce very interesting nuclides like actinium 225 and different type of radium, radon, and so on. For medical applications is rather useful. So, and for future, we consider that thorium is a main energy resources and main mother nuclides for production medicine radionuclides, radionuclides for medicine. And uranium 238 maybe there is some possibility to produce energy, but I think until we have a thorium, it's better to produce energy from thorium. And uranium 238, I think, is resources for our future, because uranium 238 have two additional neutrons in comparison with uranium 235. And if in future we will meet some interest in heavy nuclides, so uranium 238 is the first mass nuclides for production of valuable and future nuclides. So this is a scheme of reactor MSRE. So I begin from the history. In the history, the history of molten salt reactor began in 1945. So these reactors, but aircraft reactor experiment. These reactors was with power capacity, maximum power capacity about 3 megawatt, but the experience was with several hundred kilowatt. The life cycle of this reactor was about 1,000 hours, but the scientists received a lot of informations. And after this was created molten salt reactor experiments with power capacity about 7 megawatt. And the life cycle of this reactor was more than 4 years. in a power with Newton field, the life cycle was 15,000 hours. It's rather good experiment. As a result of this, utilization of this reactor was the conclusion that at these reactors, it was confirmed the operability of all the main components of molten salt reactor. Pumps, heat exchangers, system for cleaning from gaseous radioactive waste, the corrosion activity, and so on. So it's what very good beginning. And so after this question, why this experiment was stopped? It's a very interesting situation that excuse me, at that time was interesting with very high parameters of breeding. And sodium-cooled fast reactors at that time was very favorable in comparison with molten salt reactor. But nevertheless, at that time was creating a rather good project for molten salt breeder reactors. But the main nuclide for energy production was thorium, but not uranium. Uranium for beginning was uranium-235, then uranium-233. And now when we consider the detail of this project, we understand that the thinking of the time was rather useful for us now. And we can extract a lot of from this design for our future work in this direction. After this, Alan Weinberg, who was a director of this direction, was removed to another work. I have met with him in the beginning of this century in Gordon conference, and he remembered about the times and told that at that time there was not such robotic techniques for distant repairing of molten salt reactors designs, because you know molten salt have a lot of radionuclides, and if there's some faults in working of different part of designs, nobody understand how to repair it. And now when we have artificial intellect and robots, robotic technique, Alan Walter told that now he can see the perspective for molten salt reactors. It was more than 20 years ago. 20 years ago. So the history, Emerson, and so what we consider as a result of nuclear energy system development, not only energy production. Fission products of these Newton technology processes is very valuable new nuclides. And in the beginning of 90s of the previous century, Japanese scientists estimated the quantities of fission products which we will have in future for different kind of utilization. Noble neonuclides, rare earth neonuclides, and a lot of different neonuclides. Among fission products, there are 20% of stable neonuclides, very valuable stable neonuclides, and only 10% of fission products is radioactive. But now radioactive what is radioactive nuclides? These nuclides have additional valuable features which we can utilize. So Japanese scientists can consider fission products and spent nuclear fuel as a valuable resource for 21st century. So you see, we produce energy 1 gigawatt maybe, yeah, and we produce fission products, and the quantity of new nuclides will increase. And if we are going to consume 1 million ton of heavy nuclides, we will have 1 million ton of valuable fission products, new nuclides. So you see the most valuable material now is gold. But in future, we consider the most valuable nuclides will be fission products. And this is fission products. Fission products, there is not dangerous situation with them. We know the chemical features of these new nuclides. We know the migration properties of these nuclides in the earth and so on. We know the consequences of eating maybe such new nuclides. But concerning actinides, there is another practice. And the main our goals when we consider molten salt reactor in nuclear fuel cycle is controlling quantities and maybe quantities of minor actinides. So for example, if we have some process of producing of americium, so we have different strategies. If we are going to move americium for storage, we have some equilibrium quantities in future. But if we are going to close fuel cycle for americium in fast reactors, there will be another quantities. I don't know such, maybe several hundred tons. But for fast reactors, the equilibrium quantities of minor actinides will be maybe 1 ton per gigawatt electric. Plutonium, I think 10 tons per gigawatt electric. Americium, approximately 1 ton. But if we have opportunity to put americium in thermal reactors, we can reduce the amount of americium in fuel cycle. In this case, I think we will receive approximately several hundred kilograms. But if we have molten salt reactors with thermal spectrum, like MSRE, the equilibrium quantity of americium will be only, I think, less than 100 kilograms. So when we have in energy system different kinds of reactors, fast reactors, thermal reactors, molten salt reactors, for different kind of minor actinides, curium, americium, neptunium, we can choose different types of reactors for closing fuel cycle. So neptunium can be used in fast reactors and thermal reactors, and curium we can use only molten salt reactor. Americium, if we put americium in a fast reactor, we will meet a lot of difficulties. It's difficult to make economically efficient fast breeder reactors if with fresh fuel we will the same difficulties as with spent fuel. So but if we are if we have opportunity to put all minor actinides in molten salt reactor, in this case no difficulties with solid fuel reactors, thermal and fast reactors, and molten salt reactor can can operate with any content of fuel matrix. So from 1990s, my interest in molten salt reactor development was moved to utilizing minor actinides. When we consider different scenarios of nuclear energy system development, we have opportunity to estimate the asymptotic behavior of such system. In this slide, you can see asymptotic structure of nuclear energy system for uranium-plutonium fuel cycle. What is the difficulties? It's a perfect thermal reactors, very good PWR with not very big burn-up. I think maybe 30 megawatt days per kilograms, not 70 or 50, but only 30 maybe. And fast reactors, very good fast reactors with excess plutonium production, maybe 300 kilos per gigawatt year. For Brest reactors, there is no excess production, but it's very good sodium cooled reactor with metallic fuel. Breeding ratio about maybe 1.4. So, and molten salt reactor for minor actinide utilization. It's a good structure. It's maybe our goal. But now you know that about 100% we have thermal reactors. And nobody wants to increase the share of fast reactors. But if there will be no molten salt reactor, we will meet in the nearest future, in the end of the century, a rather difficult situation with minor actinides. We will have in the world, I think, about 1,000 ton of minor actinides. Even in Russia, we will have, I think, about 100 tons of minor actinides. What to do them? I don't know, because I can no image that anybody gave us a license to long-term storage or for burning of minor actinides. So now we began to develop a design of research molten salt reactor. And if the result of this experiment will be good, there is a plans to create a molten salt reactor with power capacity 2,400 megawatt thermal, with capacity of minor actinides utilization about from 2 to 300 kilograms per year. So this is asymptotic structure for uranium-plutonium fuel cycle. And the molten salt reactor is very useful for minor actinides production. But if we have opportunity to use uranium, plutonium, thorium fuel cycle, there is another situation. We can have a lot of thermal reactors, breeder reactors, not very big share, not more than 10%, and molten salt reactor will be decreased in this share of molten salt reactor will be decreased by 3 times. For physicists, 3 times, not more. But for economy situation, decreasing of very complicated reactors in 3 times is rather profitable. So our future combination of uranium and thorium, and you know that in nature we have thorium in 3 times more than uranium. So our goal to consume maybe per gigawatt electric in the new nuclear energy system 75% thorium, 25% uranium-238, and so it will be a very harmonic nuclear energy system. So, problems. Molten salt design discussed now at the time in GIF meeting. So, what they decide to do in the future, I don't know, but now in Europe, in Russia, we consider two types of molten salt concept. As for minor actinides burning and for thorium utilization. And the only working now molten salt reactor in China. In China, in this year, they have produced protactinium-233, and so thorium utilization began in this year, maybe in China, in molten salt reactor. A lot of other countries trying to do something in molten salt direction, but this is practical and this is theoretical work. So this is a table of different approach. I think that only some ideas and we think how to do such reactors. Thermal spectrum reactors with molten salt and fast and epithermal spectrum molten salt reactor. We consider the as salt carrier FLIBE, lithium fluorine, beryllium fluorine with addition of uranium, plutonium, minor actinides. But there are some scientists who wants a fast spectrum. Why there is interest in fast spectrum? I think that they are trying to consider molten salt reactor which can be in competitions with fast reactors. Which type of this reactor can consume more quality of minor actinides. And so the idea is rather simple. In fast spectrum, we can load in these reactors only minor actinides, and for everybody will be clear that if this reactor is not consuming plutonium or uranium-235, they consume only minor actinides. But the difficulties with creating of such reactors are rather principal. We can consider it a little later. So, why FLIBE? Lithium, phtor, beryllium, fluorine 2. Low neutron cross sections. So, in the energy nuclear energy system, neutron balance is a critical parameters. You know that for reactors we should have K effective equal 1. But when it's a differential feature. But when we consider energy, nuclear energy system, we should consider integral behavior of this system. In system, we should demonstrate that we have opportunity to consume all quantity of uranium and thorium which we extracted from the earth. And so there is, we have no opportunity to make experiment. It's only calculations. And we should consider neutron balance. And we consider neutron potential for this. Because if we consume all uranium-235, we will have in future a lot of uranium-238, a lot of thorium, but we have neutrons for their effective utilization. The FLIBE salt carrier is rather good for thermal spectrum. Low neutron consumptions, low vapor pressure, radiation stability, no radiolysis like in water coolant, no problem with hydrogen. Solubility of fission products. When we consider different barriers from the radiation for the radiation safety assessment, you see that molten salt reactor has a very good chemical barrier, not physical. The most quantity of fission products are rather have rather good solubility in fuel. Compatibility with construction materials, construction materials for such designs, nickel molybdenum alloys with low concentration of ferrum or chromium, and low fuel processing cost. It's only estimations. So, what we should investigate? Metallic alloy, combined coexistence, a lot of different substances, but the previous experiments with MSRE and aircraft experiment show that we have opportunity to have good technology. So, challenges for future development MSRE. Development of salt and material combination. Now we have special installations for experiment with different kind of salt composition and construction materials. And the next very important point, development of integrated models and physics and fuel chemistry in alone code. And very difficult situation in comparison with previous century. We should have a licensing processes. We should have special rules, criteria, and so on. Now we have rather good development for solid fuel reactors, but we have no such documents for molten salt reactors. And in nuclear energy, there is very difficult situation in our law environment. Any technology except nuclear can do everything which not constricted by law, but we have opportunity to create only those things which permitted the such documents. So before creating of designs, we should create law for development of nuclear energy. And physicists and chemists, and specialist for chemistry is not a specialist for creating of law. So, what we have from molten salt reactor? It's rather easy to add actinized to salt. We have no need to create special tablets or pellets for fuel. Actinides remain in salt until for total burnout without extraction from the fuel cycle. And fission products removed from salt without capturing neutrons in such amount like in solid fuel reactor. So neutron balance and consumption uranium-35 can be decreased in molten salt reactors. But research and development required a rather large scale, and in the field of law too, not only the chemistry and physicist. So there is some scheme of molten salt reactor installations, preparing of fuel circuit with molten salt, intermediate circuit with molten salt, and power conversion system. What rather good in comparison with solid fueled reactor, we have in molten salt reactor very large negative reactivity coefficient. This reactor is very stable in comparison with solid fueled reactor. And the more power capacity, the more stable such reactor is. Very good feature. So the positive characters or sides for molten salt reactor. Continuous removal of gas fission products. Continuous addition of uranium and trans-uranium nuclides to replace the lost by burn-up. And we can control the chemical situation in this molten salt composition by production of uranium fluorine 3, because the main composition of uranium for fluorine 4. But if some nuclides was fissioned, there's a free fluorine. So we can consume this fluorine without corrosion of construction materials. So uranium 4-3 is a measure to control the chemical potential in such composition. So, what is good for molten salt reactor? Rather good solubility of such fission products. So when there is some leak and so on, there is no radiation dangers from such nuclides. And uranium iodine 231, you know, it's rather it's not very good for radiation safety, but there is a rather interesting behavior of these nuclides in molten salt. You can read the details. Noble and semi-noble fission products. There are some difficulties because such nuclides is not very soluble in salt composition, and there is some not very good things. They are captured in heat exchanger. But the quantity of such nuclides is not very big, and from the point of view heat change, it's not difficult. I think we will meet difficulties with repairing or maybe after shutting down of such installations. Noble gas fission products. In solid fuel reactors, where there is some heavy accident, we have a lot of difficulties with fission gas products. But in this situation, with molten salt reactor, we can extract in with online processing, and the danger from fuel composition in molten salt reactor is less than in solid fuel composition. And some phenomena related to safety. High boiling point temperature, so low vapor pressure, high heat capacities, low chemical activity, high radiation resistance, negative reactivity coefficient of temperature for rapid response, inherent fission products retention capability, and gaseous fission products are continuously removed from fuel cell. So, I told you about main features of molten salt reactor. So, but molten salt reactor is, we consider as a part of a nuclear energy system. So, for creation of nuclear energy system, we need international cooperation. It's not a task of definite countries. We need a progress is multilateral framework, especially in creation of different codes and models. We need a lot of experiments and not any country, even China and United States, can alone create such, I think, very complicated technology. We meet new kind of technology in which we have no opportunity to make physical difficulties in reactor and chemical difficulties in fuel cycle. In this case, we meet complicated difficulties in one installations. So a molten salt reactor we should consider as a system which have multimodal difficulties, not multi-physical instrument we should have, but we should have multi-modeling instrument. And what is the difficulties now? Now we are in a time of competition on short-term issues. Our interest now is rather short-term, and we have no opportunity to make an agreement in development of such complicated technologies. What we propose? We propose to consider risks, long-term risks. Long-term risks can help us to understand each other and to create integral conditions for development of molten salt technology reactors. Because you should understand, in the nearest future, there is no benefits from such type of reactors. These reactors for solving long-term problems and for deciding of long-term problems, we should prepare the potentials for meeting these long-term problems. So molten salt reactor is rather good for joining international capabilities to create energy system, because no profit, but reduction of risk in future. So cooperation on long-term perspective, sustainability, non-proliferation, safety, and security. So for me, it's more easy to answer question, because the volume of such task, it's difficult to oversee what kind of interest you will have in this situation. So I am ready to
Thank
answer
you so
questions.
much, colleagues. If you have any questions, yeah.
Yes, thank you, sir, for your presentation. I just wanted to ask you that with all this partitioning and transmutation or burning of minor actinides is concerned, is Russia only focusing on the molten salt technology, or do you also have an option like the Belgium people are doing, accelerator-driven systems?
we consider not only accelerated driver system, but fusion neutron source too. But you see, we have to consider cost of neutron. Cost of neutron from uranium-235 in the nuclear energy, I think per 1 gram, $1,000. But 1 gram of neutrons from accelerator, $200,000. From physical point of view, good, but for energy production is not suitable at all. And cost of fusion neutrons, if we will receive this, I think $10,000. So accelerated driven neutron, very, very expensive. For science, it's good. For medicine, it's suitable. But for energy, we have no opportunity to buy such very expensive neutrons.
Thank you, sir. That actually this was a very good answer, because I asked this question earlier also to a few other people, but the way you put it, no, the cost of neutrons per gram, I think that justifies the economy of the whole system. Yeah.
It's estimation for ourselves. It's very for economists. It's not a price.
Thank you. Any more questions?
Thank you for the very nice presentation. My question might be a bit dumb one, but I would like to ask anyway. So when we are talking about the burn of these minor actinides, is it a necessary thing we have to do in order to get rid of them, or are there any possibilities that somehow these in the future will actually be useful for energy production or some other purpose?
I quite agree with you. So we have maybe we consider this in such a way. It's a very foolish thing to burn minor actinides in solid fuel reactors, PWN, sodium-cooled reactors. But if they want somebody to burn, we have no opportunity to burn, but we should demonstrate for policymakers, environmentalists that we have opportunity. It's expensive, it's difficult, but if you want, we can. But for not to but I think it's not very good to complicate fast and thermal reactors. They are expensive already. So we propose to use molten salt reactor, but our idea that the humanity will be wise in 100 years, and we will switch the molten salt reactor for thorium fuel cycle. And minor actinides only for demonstration that we can. But we have hope that we are not going to do such foolish thing. I think these nuclides are very, very valuable. I don't speak expensive, valuable. But we don't know how to utilize them.
Thank you. One more question.
I have a question about this long term. What the time schedule of this long term? Because you showed this system, including thermal nuclear reactors, fast neutron reactors, and molten salt reactors. So, and today we don't actually have the first two parts in good cooperation. Yeah, we have only two fast reactors. I would say also demonstrative BN 600 and BN 800. And so first step will be build this two component system, as I understand, and the next step will be include the molten salt reactor. What do you think the time schedule of this huge project?
when we when we first time met with our Japanese friends, you see the time. So we consider our history, our future history, till up that time. I think 40,000 years. We consider asymptotic when we have 15 million tons of uranium and 40 million tons of thorium. So maybe 40, maybe 50,000 of years for humanity future. And we consider asymptotic situation. Time and seasons is not in our power, you see. So, and we have no breeding reactors now. Fast, yes, but breeding, no. Nobody wants to have a breeding. And very interesting thing, when we consume uranium-235, we spend energy for extracting, production, and so on, maybe several electron volts or kilo electron volts with enrichment. But we receive 200 million electrons. When I utilize plutonium, for production of plutonium, I spend 1,000 mega electron volts. 1,000. So from the point of view of first thermal principle, of thermodynamic principle, is nonsense. Utilizing fast reactors now, or utilizing plutonium thermal reactors, is nonsense now. Only when I create a system with breeding ratio, more than 1, I have opportunity to utilize plutonium. So our future is not time. Our future is structure. How we can manage create a structure of nuclear energy. And if nobody wants to create fast reactors, we consider thorium is rather good for the situation. You see, future system may include evolutionary and innovative design. What I mean evolutionary? PWR. When I reduce the burn-up and power capacity of these reactors, this reactor, VVR 100, will be evolutionarily innovative. The fuel efficiency will be increased by 2 or 3 times in contemporary reactors, which we have now, only reducing burn-up of fuel in this reactor. So we can change thinking. We should consider nuclear energy as a system. When in the system, in the entrance of the system, when we consider nuclear reactors, we have a fuel with chi infinity much more than 1. But when we consider system, we have a fuel in entrance with chi infinity much less than 1. And we have neutron source, uranium-235, and a lot of energy sources, uranium-238 and thorium-232. But we should convert them into fissile neonuclides. And so the nuclear fuel cycle is a basement of this. So chemists and technologists should be main in this process, not the design of reactors or neutron physicists. Technologists and chemists should be main in these processes. It's difficult to imagine such situation. And when we have some problems, first of all, we should change thinking. And then only after this, we should do something by hands.
Okay, and about the production of energy by molten salt reactors. So I understand that the main idea for molten salt reactors is to burn the minor actinides and maybe breeding. But is there any theoretical limits for production of energy?
I think that molten salt reactor have much more opportunities for future than solid fuel reactors. Solid fuel reactors is only we try to use theories of previous technological decisions, steam generators, heatings, and so on. But molten salt reactor is principally innovative design. You know that the beginning of our thinking was a stone. In 2 million years, we learned how to do holes in the stones. Now we have neutrons, like stones. We can split nuclides, but we don't know how to make a hole in neutrons and to control the fissioning products. We only in the beginning of new nuclear technology. Neutron is a absolutely new source for future technologies. So energy is a part of system for controlling nature. Energy. Neutron, more valuable thing in controlling nature processes. So we should thinking in a new way.
Yeah, thank you. And one more simple, maybe technical question about the electrolyte itself. So you mentioned that nowadays, at least in Russia, maybe in other countries, the main composition of electrolyte is a FLIBE and not a FLINAC. What was the main pro for the FLIBE?
Yes, main. FLINAC is rather good for solubility of actinides, uranium, plutonium, and so on. And if you're going to have a fast reactors and to demonstrate that we can consume all minor actinides, it's rather good. But we have no construction materials yet. And another thing, for fast reactors, the quantity which we should operate in nuclear fuel cycle will be several times more. I think more than in this situation. Another situation, chloride. Chloride too, very good for fast spectrum too. But the problem with construction materials. But for molten salt reactor as a burner for closing of nuclear cycle for minor actinides, thermal reactors and FLIBE, the perfect substances. But we should utilize graphite as a moderator. And for fast spectrum, we should very difficult situation with thermohydraulic behavior of fuel salt inside this vessel. When we consider diameter of 3 meters and height 4 meters, what I can calculate the neutron field and heat extraction from this, I don't know. But when we consider thermal reactors, there are rather good profilation of velocity of fuel salt, and the critical concentration much less than 1%. But for fast spectrum, we need 10% and more. So chloride or other situation, but construction materials no. situation with thermohydraulic and not understable, chemical situation rather difficult, and FLAP is rather good. Fluorine, when I consider the oxygen potential, it's rather good to different nuclides. Chloride is rather not situation.
Any more questions? If not, let's thank the speaker again.
So, excuse me for not very good, maybe conversation. My English not very good for this. In Russian, I can explain in more details. Excuse me. When we worked inside IAEA with INPRO methodology, I proposed to use Russian because Russian language for system estimation is better than English. It's my practice. So, thank you. Thank you very much.
Okay. Let's go back from this very huge plans, this philosophical, I would say, topic about the future systems, so the nuclear energy production, to rather simple tasks, maybe not simple, but very technical and not so broad. And we'll talk about the head operation of spent nuclear fuel reprocessing During different lectures, you've already heard about these operations. I decided just to make some brief explanation and maybe overview of what we are meaning with the head operations of the spent nuclear fuel reprocessing. And as in many presentations, first is about the complexity of working with the spent nuclear fuel. And yesterday, when I talked about the storages of the spent nuclear fuel, the one thing that I forgot to mention also from the historical, again, point of view, that in the beginning of the nuclear era, the burn up, the time when fuel was working in the reactor was rather small. And that means that the amount of the fission products, of the neutron activation products in the spent nuclear fuel was not very large. But with the development of the technologies, development of the materials, of the reactor, of the fuel itself, of the cladding of the fuel, of different types of the parts of the reactor vessel, it become possible to have a longer time of operation of the nuclear fuel in the reactor. That means that we can prolong working of the fuel in the reactor and increase the burn up, and that means that we increase the amount of the fission products and activation products. And from the point of view of the storages, for example, that means that we need to increase the biological shielding. We need to improve this neutron capturing systems and so on. The same is for the head operations for the reprocessing of the spent nuclear fuel or irradiated nuclear fuel, because when we increase this amount of the fission products in the spent nuclear fuel, among these fission products, there are elements, chemical elements, that are not very easy to handle in aqueous solution, like molybdenum or zirconium is also part of the fission products, because they form a lot of the precipitates even in acidic conditions. And especially with, so you've heard about the Purex process, there is a use of tributyl phosphate. Due to the radiolysis, tributyl phosphate converted to the phosphoric acids, dibutyl phosphoric acid, monobutyl phosphoric acid, and they create salts with the zirconium. So there are a lot of chemical reactions with a lot of chemical elements during the reprocessing. And the first stage of this reprocessing is to convert this complex mixture of elements to the aqueous solution, because currently the main technologies are the hydrometallurgical technologies, even if we have quite a lot of good developments in pyrochemistry. Today still the main process is so aqueous and aqueous solutions of these elements. And we need to work with all this with this zoo of the elements. And first steps, as for storage and for head of operation, is the unloading of the spent nuclear fuel. And there are different techniques depending on the design of the nuclear reactor. It is this machine for unloading and loading of the fuel assemblies in the reactor. This is Erbimka type of the reactor. Probably you cannot see from the screen, but you will see later in presentations that there are people, yeah, here very small figures, and at the end of this hole, there are fuel assemblies that are hanging. So it's not a spent fuel assemblies, it's fresh fuel assemblies, but you can imagine the size of the reactor and of these assemblies. And this unloading and loading machine is transporting the spent fuel assemblies further to the storage pools, for the cooling pools, etc. For the VVR reactor, there is upper part of the vessel, and it is the spent fuel pool. So there is this unloading machine that takes spent fuel assemblies from the reactor and put it in the spent fuel pool. So the first stage is unloading of the spent fuel assemblies. And the storage that we talked yesterday sometimes looks very nice, yeah? Due to the presence of the beta emitters, high energy of the beta particles. If you remember, the energy of beta particles should be more than 270 kiloelectron volts to produce the Cherenkov-Vavilov radiation. That is visible radiation when the particles are moving faster than the speed of light in the media. So, and it looks really beautiful. Then storage, and yesterday we talked about different types of the storages. There is, as one of the requirements for all kind of storages, it is removal of the heat that is released from the spent nuclear fuel, and there are just information about the heat generation. It is kilowatt per one spent fuel assembly at different storage periods in years. So we can see that after 3 years, the heat generation decreases, let's say, 1 order of magnitude, yeah, something like that. And it is specific, not some mistakes, specific activity of this spent fuel assemblies. Again, it is thousands of curies per one spent fuel assembly, and curie, as you remember, it is 3.7 to 10 to 10 becquerels, so it's a huge activity, and it is thousands of curies. And again, so as a heat production, and heat production is generated due to the radioactive decay, as the activity is decreasing 1 order of magnitude, the heat production also decreases 1 order of magnitude. And as we mentioned yesterday, the storages can be located directly at nuclear power plants, near reactor or outer of the containment, or they can be centralized storages where spent fuel assemblies are transported from all the country to this central storage. There are wet and dry storages. Again, wet storages, they're used distilled water, sometimes with the addition of the neutron absorbing components like boric acid or something like that. In Russia, it is storages at nuclear power plants. In production association Mayak in Chelyabinsk region, and mining chemical combine in Krasnoyarsk region. Dry storages, it's a different type of storage where the cooling is done by the natural convection of the air, and the vessels with the spent fuel assemblies, they're sealed, and they contain then inert gases, nitrogen with some fraction of helium, and helium is used as an indicator of the leakage from the vessel. And we have this dry storage, central dry storage, also at mining chemical combine, as I mentioned yesterday. So for transporting, it was a lecture
last week, on Tuesday, about the transportation of the heart of the nuclear reactor. There are different designs of these transport packaging containers. Some of them can be used for storage of spent nuclear fuel, but the main goal of these containers to transport spent nuclear fuel from the nuclear reactor, from nuclear power plant, from the pool, spent fuel pool, or to the reprocessing plant, or to the centralized storage. And at the reprocessing plant, we finally start our reprocessing of spent nuclear fuel. So all this operation before, they had operations for the treatment of the spent nuclear fuel. They are not chemical directly, but they're important part of the logistic for the reprocessing of spent nuclear fuel. And the first stage before the dissolution of our spent fuel is, of course, opening of our cladding, opening our fuel rods. And it can be done with different technique. It can be done without separation of the cladding material and the spent fuel. So it is either just the simplest. It looks like simplest, but there are a lot of technical challenges. It is just chopping, cutting of the fuel assemblies or fuel rods into pieces, and then dissolution of the spent fuel in nitric acid. Under these conditions, cladding can be not dissolved. So we have, even if in the beginning we don't separate cladding material and fuel, but due to the chemical procedures, there is a separation of the cladding and the components of the spent fuel. Or we can dissolve cladding and spent fuel together with different approaches. It is either in aqueous solution with the use of nitric acid. You will see that nitric acid is the main component of the radiochemical processing, radiochemical technologies in general. It is for different reasons. The main reason that you can use stainless steel to work with the nitric acid, and actually it is very difficult to use chloride media to work with stainless steel, because steel is dissolving in the presence of chlorides. So that's why when we are talking about radiochemical operations, we, I would say, never use hydrochloric acid as a diluent or to dissolve something. Only to dissolve steel, if we have a special type of the fuel rods that are made not of zircaloy, but that are made of steel, then we use hydrochloric acid to dissolve it. But in many radiochemical operation, it is used only of nitric acid. Sometimes with the addition of some fluorides to improve the solubility of zirconium or plutonium, because they can form these complexes in aqueous solution with the fluorides, and it increases the solubility. Pyrochemical methods can be also used for dissolution of the spent nuclear fuel together with cladding. And again, as we discussed on Friday, with the use of the specific potential on electrodes, you can dissolve either actinides or zirconium or cladding or other materials. So chopping, as I mentioned, it looks like a very simple procedure, but actually for technologists it is not so, because the main challenge for all this procedures is that you should work in a hot cell. Yeah, so you cannot just go to the fuel assembly and remove, for example, one detail and put another. It is impossible, yeah, because the radiation fields are so high that you should work only remotely. And from this point of view, there are a lot of requirements for the mechanics, for the materials that are used as materials of knives or guillotines, and it is specific requirements of for these machines to be able to be replaced remotely. Yeah, so the design must allow to change these knives remotely. So it can be just knives or guillotine, so it's just direct chopping of the fuel rods, or it can be saw, so to sewing the fuel assemblies. The first operation is the cutting of the end capes, so endings of the fuel assemblies, and then either chopping of the fuel rods one by one, or with just maybe several of the fuel rods together. And the techniques that are developed today, it is plasma and laser cuttings. So again, here maybe it's not a very clear picture. So it is a hot cell. It is a window, this with LED glass shielding, so you can control what is happening inside the hot cell. It is a fuel assembly and the chopping machine. So there is these pieces that are chopped. They are going down to the next level for dissolution. Yeah, so there is just a falling down of these pieces to the next chamber that is located below this first chamber. So I couldn't find a better picture. Sorry for that, but you will see it maybe more clear in the presentation that you will have it. It is different techniques for cutting, for the opening of the assembly. So it is like banana peeling technique. So it is 3 knives that are located like 120 degrees, their positions, and they're going through the assembly with small rotation. So, and the cover of the fuel assembly is opening like a banana. So, and there is a removal of this external part of the fuel assembly, and then you can take the rods, fuel rods, one by one. So it is saw to remove the caps or endings. Then the fuel rods can be cutted one by one. So it's a special knife, like rotating knife, and chopping these fuel rods. Or it can be several rods that are chopped together with the guillotine. Yeah, you can see here it's a guillotine. Or there is a special knife that can cut the pack of fuel rods together. And again, different techniques to remove this external part. It is not only banana peeling, it can be just one one cutting and then opening of this cover. So depending on the design of the fuel assembly and what technology the facility have. It can be different instruments at one facility. So again, for different kinds of assemblies. So laser cutting, that is so a lot of interest now for future reprocessing plants in Russia, for example. It is very good technique because you can cut precisely every fuel rod. So there is a special, I think it is not mentioned here. Yeah, it's only, so it's only the laser system itself, but before cutting, there is a special mechanism that take the fuel rod, so it's fixed fuel rod, then you have two cuts, and then take these fuel rods for further operations. So it can be very efficient. Nowadays, these operations, they are already tested with not spent fuel rods, with the fresh fuel rods. Now there are a lot of questions about the formation of the aerosols for the gas treatment of this technique, but it seems like it is possible to avoid the formation of the aerosols of the spent fuel. So this cutting can be very precise and efficient. And also, there is no need to cut the fuel rod through completely. So it's enough just to make a small, how to say, cutting, small line in the fuel rod, and then you can just break the fuel rod. So there is no need to completely cut the fuel rod. Okay, so and why it is better to separate cladding material. So first of all, as I mentioned, the cladding itself consists of elements that can form precipitates, for example, during the reprocessing, like zirconium. A lot of problems with the zirconium. So during the reprocessing, during the first cycles of the extraction, we need to add special aqueous water-soluble ligands to avoid extraction of zirconium in the organic phase. So better to avoid the presence of zirconium in the solutions. It is problems with the salt, with the radioactive waste that are formed after the reprocessing of spent nuclear fuel. So if you have a lot of salts inside your solution, inside your radioactive solution, that means that at the end you will have a lot of radioactive waste that must be immobilized, and that must be treated, storage, and finally disposed. And the more salts you have, the larger the volume will be at the end of your process. So it is better to avoid to separate cladding material from the components of the spent nuclear fuel. And to do this, we can use different, again, techniques, selective separation and dissolution of spent nuclear fuel and cladding. For example, like here, steel, it was testings when it was found that steel cladding can be dissolved under this conditions selectively and can be removed from the nuclear fuel. Another approach is the dissolution of the cladding in liquid zinc during the pyrochemical separation. Okay. There is an example of embrittlement of the cladding. So to make it embrittle, very хрупкий, I forgot the word. Fragile, yeah, thank you. Very fragile. The zirconium is known to be not stable under the action of hydrogen, under the action of nitrogen. The structure of the zirconium in the grain boundaries become very fragile. So with the heating of the fuel rods in nitrogen atmosphere, the zirconium become very fragile and can be separated from the nuclear fuel. And nuclear fuel, if you remember, it is just pellets, ceramic pellets of uranium dioxide, and they are very stable. So it become possible to remove this powder of the zirconium alloy from the spent nuclear fuel pellets. So as I mentioned before, the first operation for disassembly of the fuel assembly is the cutting of the endings of the spent fuel assemblies, and then these openings of the spent fuel assemblies and cutting of the fuel rods. So what after this chopping, cutting, laser cutting, whatever, when the next step is the dissolution of our spent nuclear fuel. There are several chemical reactions that are written in a simple way. Of course, the reactions are much more complex. So the dissolution, again, you can see here nitric acid again. So from 6 to 8 molar nitric acid at elevated temperatures, dissolution for few hours, and uranium and plutonium goes to the aqueous phase and fission products as well. Not all of them, but most of them goes to the aqueous solution. And as you can see, there is a formation of a huge amount of the nitrogen oxide gases. So for the off-gas treatment, in this case, there is need of capture of this nitrogen oxide with different scrubbers, with the caustic scrubbing as well. There is, of course, the release of iodine under these conditions of the under heating in nitric acid solutions. So we need to use, as I mentioned yesterday, the most effective systems, absorbers. They are silver containing carbon or zeolites or silica gels. There is a need to catch the tritium, a huge amount of tritium released here. And of course, noble radioactive gases that can be captured with the cooling of the gas stream, with the absorption of these radioactive gases into charcoal or some other technique. So what we also need to take into account is nuclear safety, because water is the moderator of the neutrons, and that means that we cannot have a high concentration of plutonium in the solution, and also the shape of the vessels should be specific. It should be not a like a sphere. That's a very bad shape for radiochemical reprocessing. Usually these vessels, they are made like thin vessels where the nuclear safety is provided. So for the dissolution of different types of spent nuclear fuel, we always use the same diluent, the nitric acid as a universal dissolver for any kind of the fuel. MOX fuel, the problem with the MOX fuel is that the plutonium dioxide is very difficult to be dissolved. Even if very often when we write or read scientific papers, you can see that uranium-4 and plutonium-4 they can be considered as analogs, chemical analogs, the same oxidation state, very close ionic radius, they are located very close in periodic table. So you can investigate the chemistry of uranium-4 and say that plutonium-4 will behave in the similar way. It is not true, and it is a good example when you can dissolve uranium dioxide just with the hot nitric acid, and you cannot dissolve at all plutonium dioxide under the same conditions. To make it possible to be dissolved, there is addition of the fluorides, because plutonium form the soluble, aqueous soluble, water soluble complexes with the fluorides. You can add oxidizing agent. It is silver +2. You can see here, and silver +2 can be produced with the electrochemical reactions. You can add iron-3 also as oxidizing agent at high nitric acid concentration, or you can use anodic dissolution. So different types. Today, one of the most promising, I would say, way to dissolve MOX fuel is the use of silver +2. Because you can recycle silver, it will be reduced to silver +1, then you can oxidize it again and use it again. So nitrate fuel is very easy to be dissolved again if we are talking about the uranium, but there is a formation of the this oxide of the nitrogen +1, and it is oxidizing agent, like not like oxygen, but it can be used as oxygen, so it can be a danger flammable situation with this oxide. So there is additional treatment of gases to avoid the formation of this oxide in the air. Carbide fuel. The problem with the carbide fuel is the formation of the different organic compounds with the dissolution in nitric acid. So for further reprocessing, we need to remove these parts from the solution. Then the solution clarification. So after the dissolution of spent nuclear fuel, the solution itself is not a pure clear solution. It's more like a suspension of different particles. It is undissolved cladding materials. It is construction materials of the fuel assembly, including stainless steel parts of the fuel assemblies. It is undissolved parts of the spent nuclear fuel, so we have to separate it and put it again in the dissolver, because from the many points of view, from the economical point of view, from the regulatory point of view, we cannot lose any of fissile material. Yeah, so we have to completely reprocess all the fissile materials. So this undissolved spent nuclear fuel goes back to the dissolver. There is a formation of the precipitates that I mentioned several times of zirconium with molybdenium. It is a big one of the main problem during the reprocessing of spent nuclear fuel, at least in the head operations. So we need to remove it. And it is different components of the spent nuclear fuel that form metallic phases, like epsilon phase, that consists of the noble metals with the some fraction of technetium and molybdenium, and these metallic noble metallic particles, they are hardly dissolved in nitric acid, so there is additional procedures can be done, but ruthenium, for example, is very difficult to dissolve. And carbon also can be not oxidized completely, so there is particles of the carbons. To make the solutions clear for further reprocessing, to remove all these particles, different techniques can be used. It is either centrifugation, filtration with the use of tangential filtration, with the use of membranes or some specific filters, and very often several equipments are used one after another to remove particles from big sizes, from, let's say, millimeter sizes to micron and nanometer sizes. And one of the techniques that again was developed for a new reprocessing plant is tangential filtration. So it allows to concentrate these particles, these suspensions from the solution up to the slurry with the concentration of up to 100 gram per liter. And the rest of the solution contains less than 0.1 gram per liter of the solid particles. So it is an example from the test operation of this equipment. So the after the filtration, it is the concentrate, so this slurry, and it is the solution that goes for the further reprocessing. So again, you can see that when we talked a lot of different reprocessing strategies, different approaches for the design of the extractant molecules. It is very good and fundamental science and approaches, but when we go to the facility, to the plant, there are a lot of technical challenges that what we meet, and there are a lot of operations that looks very simple in normal laboratory conditions, but when you are working with the highly radioactive solutions, they become not so simple, because again, you cannot just come to the equipment, move it, clean it somehow, filter it with the hands. Yeah? All the operations must be automated and in a remote mode. The modification of the first head operations is the oxidation of the spent nuclear fuel in gaseous media that is called vol oxidation, volume oxidation of the components of the spent nuclear fuel. And the vol oxidation can be performed after the cutting or chopping of the spent fuel assemblies, but before dissolution. The main idea of the wall oxidation is to remove a significant part of the volatile components and especially of tritium because again, tritium is located in spent nuclear fuel, and when you dissolve spent nuclear fuel in nitric acid, the whole volume of the nitric acid will contain tritium. So immediately, even if you remove all other components, tritium cannot be removed from the aqueous solution in a simple way. So immediately you have a radioactive waste. So all your aqueous solution will be a radioactive waste. But if we remove tritium in the very beginning and concentrate it somewhere else, then our nitric acid solutions, for example, can be recycled many times without any problems with this radiation from tritium. There is a removal of noble radioactive gases. Again, krypton, xenon, argon, all these gases will go from the spent nuclear fuel and the carbon-14 as well. It is at temperatures below 500 Celsius degrees and above 500 Celsius degrees. Other semi-volatile components like cesium, molybdenum, technetium, iodine can be removed as well. And again, today for the new reprocessing plant for the nitride fuel, it was already demonstrated that this wall oxidation techniques, procedures can be very efficient. The removal of tritium is close to 100%, and the removal of carbon-14 also very efficient, around 98-99%. And again, small photo, there is a small ring here. It is a fuel rod, yeah, and it is demonstration that the spent nuclear fuel can be easily separated from the fuel rod, from the cladding itself. And it is examples of different vessels for these wall oxidations procedures. And also, what is important for the wall oxidation procedures is the oxidation of the uranium dioxide to uranium-308. Why it is important? Because first of all, uranium-308 is much easier for a dissolution, so it dissolves faster and easier. But also there is a change in the crystal structure. That means that if you have radionuclides that are trapped in the crystal structure of uranium dioxide, and I remind you that our initial fuel, it is uranium dioxide. So all the fission products, they are produced inside the uranium dioxide particles. So, but if you change the crystal structure, yeah, you somehow open the crystals, and it makes it easier for volatile fission products, for gases to be removed from this material. So the efficiency of removal of all these components, they are also controlled by the changes, transformations of the crystal structure of the uranium oxides. Okay, and just so it was all about the head operations. So again, it is unloading of the spent nuclear fuel, then storage it in nuclear power plants, spent fuel pools, cooling pools, then transportation to the spent nuclear fuel reprocessing facility, and then chopping or somehow cutting of the fuel assemblies and dissolution of the fuel, or maybe wall oxidation of the fuel, dissolution and we are stopping here. Yeah. So the next operations, extraction, oxidations, different operations, they are already been discussed. Yeah. Last week, all this Purex process, new process like Urex, Unix, Tollspeak, and other processes that we discussed during the last week. So the head operations, we finished them. And I just would like to say a few words about robotics and unmanned production. So the production without people. Unfortunately, my colleague from the Institute of the Robototechnics and Cybernetics couldn't come, but I took just a few slides from him, from Igor Dalyaev. So, from the very beginning, a robot itself is a machine that is programmable by a computer and capable of carrying out a complex series of actions that is important automatically. Yeah, and today we know a lot of examples of different robots, even in our houses. Yeah, we have this vacuum cleaners in many houses, and we are very impressed with the videos from the Boston Dynamics, for example, yeah, where they have this Atlas robots, and with especially the new generation of these robots. So the robots in industry and in common life, let's say, they are not something very new. Yeah, but again, for radiochemical applications, it becomes more challenging because radiation degradation of the materials, of the electronic parts of the systems, they are destroyed with the radiation, and it is very difficult to make a good robot that will work in radiation fields. And but today we have a lot of examples of the robots that are working very well in industrial applications, but all these industrial robots, they are working in a very specific conditions, in the rigidly tight, as it is written here, technological environment. So they know what to do at this specific place. There is no a lot of freedom, yeah, of operations outside of this place. And it is one of the example how robotics can help to work with the radioactive materials. It is the evolution of the manipulators for the use in the hot cell, yeah, from the very simple ones to the advanced manipulators. And what I would like to mention, that today the use of robotic arms, robotic how they call, let's say, hands, developed very much for the radiochemical applications. They are not currently used a lot, but the progress is very impressive. And again, these robots, these automated systems are very familiar in industry. This fabrication of cars, for example, is a lot of robots are involved in these operations. So the idea is to use maybe similar approaches for the radiochemical operations, and to make it safer and faster for radiochemical applications. So there are several examples of the robotic devices that are developed in Diacont, for example. It is all of them are Russian companies. This RTK, it is this Institute of the Robotics and Cybernetics. It is NPF Sosny in Dimitrovgrad, so it's not from Belarus, it's from Dimitrovgrad. So different systems that are already developed, constructed, and I would say they're waiting for the real application at the reprocessing plant. And tomorrow it will be more about the digital technologies, digital applications for the radiochemical facilities. I just here would like to mention that all these robotic systems and the design of the new facilities, they are using not only robotic system itself, but it is a system, a technological core or technological platform that combine all the units together in one system to make all these operations efficient and fast. That is good for economics. Yeah, this is all from me for today. Here, I wanted to put a video from the Sirius site where the Rosatom already made a demonstration system with all these robotic systems that are started from the compacting the fuel pellets, putting them in the fuel, controlling them, putting them in the fuel rods, and assembling the fuel assemblies. But I couldn't find it easily in internet. I asked my colleagues to send it to me, but no. maybe later they will send me and I will send it to you. It looks very nice, and it means that very soon we will have this system in real facilities for real applications. So thank you for your attention.
Questions? Everyone is tired, I suppose. Thank you so much. Very nice video.
So now we have a bus at 5, so we have several minutes to relax, and then you will go for the dinner.